Oh, now it's being recorded. We're given co-prime, sorry, let's click on the Zoom thing, integers, A and B. So I think at the beginning of this seminar series, you had an introduction to SIDH, in which it's possible that A and B were chosen to be prime powers, or specifically powers of 2 and 3. But you can phrase the problem a bit more generally in terms of any A and B, as long as they're co-prime. 2 supersingular elliptic curves E0 over FP squared and EA over FP squared. So this is sort of hinting towards the crypto system root of this hard problem. E0 is going to be some sort of publicly known starting curve, and EA is going to be Alice's public curve. Connected by an unknown A isogeny, right? So that's an isogeny of degree A. The unknown is going to be, would be Alice's secret in the crypto system framing. So let's give that a name, phi A. And so far we haven't used any torsion, but in particular, you're also given the restriction of phi A to the B torsion of E0 recover anisogeny phi A satisfying these constraints. Okay, so I have purposefully said anisogeny here and not the isogeny. If there were another isogeny satisfying the same restrictions, recovering that would also be sufficient to break SIDH. So this is really the problem that we care about. So this is a version of the isogeny problem. So when cryptographers working in isogeny-based cryptography talk about the isogeny problem, they're typically thinking about, given 2 supersingular elliptic curves over a sufficiently large finite field, find an isogeny between them. This is obviously a lot more specific than that, and you're also given this extra information on the torsion, but it's phrased in this way so that it's really the problem underlying the thing we care about. So what's the history with this problem? So this was introduced in 2011 by Zhao, DeFeo, and Plu in their paper introducing SIDH. And until 2016, it was believed that the best, the most efficient way of solving this problem for any sort of sufficiently large choice of parameters, any algorithm would cost about the square root of A in finding these and finding such an isogeny. So in order to give a little bit of intuition as to where the square root of A comes from, think about A now as a power of 2. You've probably seen some pictures of isogeny graphs by this point in the series. So your supersingular isogeny graph is this very connected graph with a degree 3. Each edge in the graph is a 2 isogeny. So if you are trying to find, on the generic isogeny problem, forget about the torsion for the moment, you're trying to find an isogeny between 2 points in your graph, you can do, so you know there exists a path of length A, so that's going to be 2 to some power, and you can do what we call a meet in the middle graph walking algorithm, where you basically compute random walks from each endpoint lots and lots of times until you hit. Or if you like, you compute all the paths from each endpoint until you hit. And so from each end, you're going to have to take half of the number of steps. and the complexity of computing an isogeny of degree a to the half with the algorithms that were known at the time is about a to the half. So that's where that comes from this meet in the middle algorithm. So it's a sort of generic algorithm that's not using these torsion points. It's just using that you're trying to find a generic isogeny between two generic curves. I saw there was a comment, but I think it was a reference for people.
Yeah, I was just posting a reference to the paper you mentioned, and I might keep doing that, so feel free to ignore them.
Okay, thank you, Drew. That's great.
Also, the red pen doesn't show up as well as the black one, so.
Oh, okay, thanks. How about I'm going to try green. Is that better? I'll stick with black, but
Yeah, maybe stick with black.
I'll stick with black. Okay, fine. All right. So that was the situation before 2016. So then in 2016, we had the first attack that was really making use of this torsion point information, which is due to Galbraith, Petit, Shani, and T. So they gave a polynomial time active attack. So I know that many people in the room won't be familiar with these sorts of cryptographic terminologies, so let me quickly say what that is. So an active attacker who's trying to attack a cryptographic protocol is someone who can interact with the players in the game. So if Alice is wanting to share a key with Bob, then, well, basically Bob can say to Alice, I want to share a key with you, and Bob can do something malicious in the generation of the information he sends to Alice. And this is the idea behind this active attack is basically that Bob is able to recover small bits of information by sending malicious torsion points. But if he does that over and over again, he can actually recover the whole key. But there was a sort of easy mitigation to this. I mean, it did reduce the functionality of the scheme, but you were still able to do message encryption with it. And then in 2017, Petit, so Petit was also an author on this 2016 paper. In 2017, he gave a polytime passive attack, but it only applied to certain parameter sets. So it didn't. It solves certain instances of this problem, but not the ones that were being considered for psych for the NIST competition. So the parameters that Petit attacked would only apply when B was bigger than A to the 4 was bigger than P to the 4, and the J invariant of E0 is 1728. And he was focusing on J invariant 1728 because this is the case in psych. But unfortunately, well, or fortunately, I don't know, depends on whether you're trying to destroy stuff or create stuff. This imbalance here was way off what they're doing in psych. So in psych, you have B is about P to the 1/2. But you do also have the J invariant of E0 is 1728. And the reason that this choice was made here to have this sort of balance between the parameters is purely for efficiency, but it turned out to be good for security as well. So that was the sort of first passive attack idea that was really using these torsion point images, and the attacks that Luciano and I developed, and also the attacks that Wouter and Thomas developed, are actually using the same underlying idea as this in some sense, but going to higher dimensions solves the problems that we had with this imbalance here. Okay, so one more before we get to this year. So in 2020, so this is actually kind of a funny story. So I had been looking at my postdoc together with Lawrence Pani, who was a PhD student at the time, trying to break SIDH. And we we're talking to Christophe a lot about it, and we sort of talked to more, Christophe Petit that is, we talked to more and more people as time went on, and we kept trying to improve this balance. And so we ended up sort of pushing Christophe's ideas as far as they could go and coming up with sort of new ways of improving them with a whole load of people. I'll just put the initials. So it's Victoria De Caen, Peter Kutas, Chris Leonardi, myself, Lawrence Pani, Christophe Petit, and Kate Stanger. And we basically showed that if you go anywhere away from this balance, you'll do better than this A to 1/2. So if you allow for quantum attacks. But it meant that we could attack everything except for the thing that people care about, which was sight. And actually, that we also showed that if you choose, you can also sort of choose a malicious starting curve where you get a better attack and these sorts of things. So the starting curve does make a difference. So that's where things were at the beginning of this summer. So then we get to 2022, some of which you already know. So both Luciano and myself, and of course, as you already know, Wouter Kastrick and Thomas de Groot came up with so on the SSIT problem with this generic starting curve, both of our attacks are classical attacks and sub-exponential. So if you're not familiar with what sub-exponential means, the relevant thing here is if you suppose that A is about 2 to the n, then the attack is about 2 to the square root of n. And so before, where we had, well, 2 to the n over 2 becomes 2 to the square root of n. So when you're looking at sort of cryptographic size parameters here, you're going from 2 to the 512, so that then an attack of 2 to the 256, so an attack of 2 to the 128, to an attack of 2 to the, I don't know, 24, I think it is, or something. I can't remember anymore, but something like that. I'm sure other people in this room are better than me at estimating square roots in their head, but it's a big difference. But Wouter and Thomas went further. They did something smarter, which is they also looked at the specific case of J E0 is 1728, and here they also give a polynomial time attack in that case, and you've already heard about that 2 weeks ago, 3 weeks ago, whenever it was. And then about a week later, Damien Robert came and blew us all out of the water and broke the whole thing in polynomial time, classical polynomial time. So it's now kind of well and truly broken. And since then, there have been a couple of suggestions for mitigations, which have then also been broken by Christophe Petit. So I'm not quite sure what the current state is. It's so hard to keep up because it changes by day, to be honest. But that's kind of the story until now, which I wanted to just spend a little bit of time on before I go into the nitty-gritty details of how this actually works. Okay, so I'm going to probably introduce this in a completely different way to Wouter because, well, I'm introducing it in the way it came about for me and Luciano rather than the way it came about for them, which is I'm first going to tell you actually about Christophe Petit's attack from 2017, and then show how going up to abelian surfaces rather than elliptic curves helps to solve the problems that Christophe Petit came up against, because well, I find that helpful. I am going to attempt to fit it on this side of the board so that I can keep the problem up, but we'll see how we go with that. I might give up halfway through. I do have a giant blackboard in my living room, but the baby got the monopoly on the living room, so I'm in the office instead. Okay. All right. So here, Petit's attack. So let's look at this problem and see what we're given. So remember, his attack is really looking at J invariant 1728, and we'll see why as well. So we're given elliptic curve over FP with J invariant 1728. That is super singular, so you know P has been chosen so that this is super singular. In all real instances, I think it's chosen to be 11 mod 12. We're also given some other elliptic curve over FP squared. There's no way I can fit this on one board. Anyway, we'll start with this. So this is the E0. We're also given this EA. We're given some generators of the B torsion of E0. And we're also given the restriction of phi A to this B torsion, which it is enough to have phi A acting on PB and phi A acting on QB, because this is the basis of the B torsion. So this tells us the restriction of phi A to the whole B torsion of E0. So this is what we're given. So we want to be given this information. We want to be able to reconstruct. We want to be able to compute phi A. So the basic idea of Petit's attack is to construct an endomorphism on the elliptic curve EA of degree B. Now, I'm not sure how much you've heard about the endomorphism ring problem already in this seminar series, or in your life, I suppose. So given a random supersingular elliptic curve, compute its endomorphism ring is as hard as the isogeny problem, not the SSIT problem, but find an isogeny to one where you know the endomorphism ring and deduce it from that. So if we're just given this random supersingular elliptic curve here, in principle, we don't know any endomorphisms on it except for the trivial multiplication by an integer endomorphisms. Even the Frobenius is just multiplication by an integer because it's defined over FP squared and it's supersingular. So the Frobenius is just multiplication by minus P. Or P. I always get that wrong. Anyway, the Frobenius is multiplication by an integer. So we don't know any, a priori, we don't know any non-trivial endomorphisms on EA, but the idea is to use these special points here that we're given to construct one. And because if we can then construct this endomorphism of degree B, then we can deduce everything we need to know. I'll show you how. So what do we know about E0 and EA? We know everything you could ever hope to know about E0. We know it's J invariant, we know it's full endomorphism ring. This is a really nice curve that we know lots and lots of things about. So on E0, we can construct as many endomorphisms as we like. So let's say iota is some endomorphism where we have all the freedom in the world to choose what it might be. I'll tell you what I'll choose in a minute. Now, we also know that there exists an isogeny between these two things, phi A. We don't know it, but we know that it exists, and we know its action on the B torsion. We also know the same thing about the dual isogeny. And so what we're going to do is we're going to take our endomorphism theta to be constructed from any endomorphisms we like on E0. There's phi A and phi A dual, and perhaps some multiplication by an integer over here as well, which we can also do very easily for any curve. Oh, wait, that's not going to be done in it. I'm going to do the D afterwards, because the picture is nicer like this. So our theta is just going to be the composition of all of these things that we know. If it's of degree B, then we know it completely because we know the action of phi A on the B torsion. And if it's not of degree B, then we don't know it because we don't know these phi A's. Okay, so how do we use this? What we're going to do is we're going to choose theta using this commutative diagram here. So it's going to be phi A dual followed by some endomorphism on E0 followed by phi A, and then we're going to add multiplication by some integer D as well to give us a bit more freedom, such that the norm of theta is equal to B. That's the main idea here. Okay, now I'm going to go over that. Got some spray stuff somewhere. Hope we're done with it. Okay. Okay, so how do we do this? Well, again, we know everything we could ever want to know about E0. So you already saw about how to like exploit endomorphisms of E0 in VaNTAGe talk. And it's the same thing that Christoph did, really, in terms of the sort of exploiting the endomorphism ring to do these tricks. So we want to choose iota in the endomorphism ring of E0. So what does this contain? Because it has J invariant 1728, it contains the endomorphism I, which is the one that takes xy to minus xiy, which we can associate with I because if we do it twice, we get minus. So we think of it as the square root of minus 1. It also contains the p power Frobenius because it's defined over fp rather than only fp squared, which I'm going to call pi. Pi is the square root of minus p. And of course, it also contains the product of those things. And it also contains all of the integers, right? That's just multiplication by an integer. Now, it turns out that at least for the methods that Christoph came up with, we don't really know how to use this bit here. So what we do, it's actually index 2 in this thing, but the denominators just make things more complicated. So what we do is we choose iota is, let me get my A's and B's in the right place, A I pi plus B pi plus C I, where A, B, and C are some integer. And then if we plug in our iota into this theta, we know the norm of theta because we know the degrees of all of these things. So the norm of theta, I can't write norm, hopefully that's clear enough, is equal to, well, we're going to get a d squared from that bit over there. That's the easy part, plus a squared times the norm of iota, which is the same thing as d squared plus a squared. And if you work this out, then you get a squared p plus b squared p plus c squared. Okay, so why am I doing all of this jiggery pokery? Well, the reason is that if you remember what we're trying to do is we're trying to construct an endomorphism of degree b. Or in other words, an endomorphism, if you're thinking of it as an algebraic integer, of norm b. So what you need to do to choose iota well and d well is to find integers a, b, c, and d that solve this Diophantine equation. So this is the problem you end up with, is solve this equation for a, b, c, and d. And so this was Christoph's kind of innovation, was to come up with this thing. But well, if you look at it for a second, you'll realize you've got a lot of very positive looking things over here. And you want, in psych, if you remember, a and b are about the same size, and p is also about the square root. So the square root of p is about the same size as b. So for the psych parameters, this thing is never going to have a solution, just because the right-hand side is too big, b is too small. So that's why Christoph's attack only applied to these sort of unbalanced parameters, is because it's like, well, it doesn't have a solution, but if b happened to be really big, then we'd be all right. That's the basic idea behind it. And the sort of moral reason behind that is that we don't have enough flexibility in the endomorphism ring of E0. And this is where the new attacks come in. It's, well, so very roughly speaking, we don't have enough flexibility in NE0, or if you like, the problem can be phrased as there's no degree B elements in NE0 when we have the parameters as in psych. So A is about B, is about P to the 1/2, and the J invariant of 0 is 1728. So it's all well and good doing all of this framework, but if this thing doesn't have a solution, then you can't run the attack. So that's the basic idea there. But here's the idea that I guess Luciano came to me with in July or whenever it was, hey, what about instead of looking for degree B elements in ND0, why don't we look for, instead of looking for sort of B endomorphisms, why don't we look for BB endomorphisms in the endomorphism ring of E0 cross EA? So this was his first sort of suggestion as his solution, which doesn't quite work, but it sort of almost worked, is looking instead at BB isogenies in the endomorphism ring of E0 cross EA. So you can do better than you can here, but it's actually still not enough to reach these parameters. You get the same kind of wall where you have this unsolvable equation. Now I'm phrasing it this way in hindsight because Damian's, it was Damian who phrased it in this way really in his paper in August, Damian Robert, who figured out that you can do this if instead of going to end E0 cross EA, you go to end E0 to the 4 cross end EA to the 4, then you do get enough flexibility and you have these degree B endomorph, degree B or B to the 4, B to the 8, whatever, endomorphisms occurring. But that's not what I'm talking about, although if I have time at the end, I might give you a little idea of how it works. I'm talking about how to fix the dimension 2 case. So this doesn't quite work, but you do get the BB isogenies between known products of abelian surfaces, from which we use a theorem due to Carney, which Luciano and Wouter and Thomas were studying together for a different project, which is kind of how all of this came about, I guess, in the first place. Okay, so I'm going to rub this out. I can tell you about that. But one answer to this problem is, why go to 2 dimensions when you could go to 8? And the other answer to this problem is using this theorem by Carney, which is what we did in our work. So Carney's theorem, I'm not really going to state it, but more tell you what it gives us. It gives a construction which is a sub-exponential time construction, which is where this sub-exponential came from in the algorithm, of a new elliptic curve, which I'm going to call EF. Well, 2 new elliptic curves, sorry, EF, and this is horrible notation for a talk. I'm going to change it, and I'm sorry for all the typos in advance. EF and EG over FP squared. Right? So we can't do an endomorphism from E0 across EA, but maybe we can do something with 2 more elliptic curves that we know, which is also enough, such that there exists a BB isogeny from the product of EF with EA to the product of E0 with EG. And then where Petit's trick will apply again. But this time is going to apply with balance parameters. Because there's enough choices of homomorphisms of this shape that you're going to be able to construct one of the right degree. Okay, so let's think about how this fits in the framework that we've already seen. So as before, what are we given? So if you remember before, we were given an E0 over FP such that J invariant was 1728, but actually now we can do something better. We're given an E0 over FP squared, which is super singular, and otherwise we don't know anything about it, including the endomorphism ring. And then we're also still given the EA, which is corresponding to Alice's public key, over FP squared, which should of course also be super singular. We're given generators of the B torsion on E0, and otherwise wouldn't be solving this torsion problem. We're also given the image of phi A, in an image under phi A of the B torsion points. Okay, so otherwise, apart from making this more general, saying it works for any E0, this is the same setup we had for Petit's attack. And then where Petit's idea was to construct an endomorphism of EA, we're now going to construct one of these homomorphisms of the right degree. So the idea is, sorry, am I covering that? To construct the BB isogeny from EF cross EA to E0 cross EG. So let's see how this fits into a nice pretty picture like we did for Petit's attack. So what did we say before? We said, well, we have E0 and we know all the endomorphisms we could ever care about on E0. So here I had a iota and I said we can choose any iota we like. Now, if we want to do this for general E0, this is no longer true. I mean, we could choose iota as an integer, but that's it. So we don't have this, but what we do have is we have from Carney's theorem, we can choose any isogeny of degree f that lands at E0. So this is about this constructing this EF such that this is going to work. So this thing we do know. We also still, of course, have our phi A in principle. I mean, we don't actually know it. We only know the action on the B torsion, but we're going to use it to construct something of degree B. So just like before, that's going to give us everything we need. And well, the thing that we're really going to learn about is this sort of induced map here, which is just the composition of this phi F and this phi A from the Carney's EF to Alice's EA. And then you've also got some more things floating around which come from Carney's theorem, which you don't need to worry too much about, but I'll put them there just so got my notation is all messed up, sorry. So this stuff is all floating around, and we're given phi F and we're given phi A, and the rest of the stuff comes from Carney. Well, phi F also comes from Carney. Now, suppose that we're in the following scenario. We suppose that F, which is the degree of phi F, is B minus A. Okay, so here we're making an assumption that B is bigger than A, but of course, if B is not bigger than A, then we can just switch them around. So that doesn't matter. They're co-prime, so they're not the same. And then what do? We choose, using Carney's theorem, we choose or we construct EF and phi F. And then by Carney's theorem, what we get is that we get a BB isogeny defined by this matrix phi, which is going to be a BB isogeny from EF cross EA to E0 cross EG. So from EF to E0, we have phi F. From E0 to EA, we're going to have minus the dual of phi A. And then on the other bits that we don't really care about, we get these other parts of this diamond here that we've got floating around. So this is going to be a map that's sending EF cross EA to E0 cross EG. So Carney's theorem says that if you have a configuration of isogenies like this, then this phi, this matrix phi, defines a BB isogeny. So it's making sure that F is B minus A. And furthermore, not only is this thing a BB isogeny, so not only does it exist, but Carney's theorem also tells us exactly what the kernel is. And so if we have the kernel, then we can compute it, which is what we care about. So I'll write down the kernel. So the kernel is the A times all the points in the B torsion of EF, and this phi applying to all the points in the B torsion of EF. Okay, and I said, if we have the kernel, we can compute it. Okay, do we have the kernel? I mean, I can write it down, but that's not the same as knowing it. We can compute a basis of the B torsion of EF, no problem, because we know EF. And we know A. So A times P is easy. What about phi times P? Sorry, phi of P. We know phi F because we chose it. So that part's fine. Now phi A of P, well, P is the B torsion on EF. So the image under phi F of the B torsion is the B torsion on E0. So that means that, as we know the restriction of phi A to the B torsion, we also know the whole of phi P. So this is known. So what do we do? Well, what do? We compute this phi directly from the kernel. And if you can do that, then you can just read off the secret actually, because it's part of phi. So then you deduce minus phi A hat. So once you've found your phi F, this part, the computing this phi, if you can make some nice choices, even for sort of what were considered to be cryptographically safe parameters, this can finish in a few seconds. But the computing of the phi F is a really tricky thing to do. So if you have something known about the endomorphism ring, then you can use tricks like you learned about from VaNTAGe to do that very efficiently. Alternatively, which is the sort of tricks that we talk about in our paper, you can try and get a nice choice of F by adding in a little bit of brute force. So you can try and find a picture like this where you don't quite find EA, but you find something close to EA, and then you figure out the last few steps by brute force. Or you can split up your phi F in 2 bits, and there's all sorts of tricks you can do, which I won't go into because I don't really have time, although I'm very happy to answer questions on that. But essentially, by pushing these tricks as far as we think they can go, and by talking to Luca De Feo about it at ANTS, we're fairly sure that if you make all of these sort of brute force choices in the best way possible, so that you can construct your phi F in the best way possible, then this becomes okay. We know that you can then do a sub-exponential attack, so that was the 2 to the square root n. What we don't know is that you can't do better, but I'm fairly convinced that you can't do better with this method. And so in our paper, we have some tables of numbers that you can use. So of course, if you're using J variant 1728, then you should just use the tricks that you learned from Wouter and Thomas. But if you're using for a generic curve, for some toy parameters, so we were looking at sort of, what's this? I don't know, probably a 30-bit prime or something. We were finding these secrets in about 2.74 seconds. So that includes this part where you have to compute this phi F. And for the lowest set of parameters that were being considered for standardization, we were looking at sort of about 2 to the 25 order of 2 to the 25 operations of brute force. We haven't implemented it. We have implemented it, but we haven't run it for the cryptographic size parameters because, to be honest, Damian's attack will be better. So we've run it for the toy parameters to check all the correctness and all the tricks to make the brute force work and so. But in order to run something of that size, we probably need some like parallel computing and expensive computing time, wasting energy and resources of the planet. So we decided not to do that and just do the toy parameters and give a complexity analysis for those sizes. And maybe I can just say a quick word about how Damian solved all of the problems in the last 2 minutes. So it's the same idea of attack of, I mean, that's where he came from to start with, except what he realized is, as I said, the problem is that you don't have enough space in the endomorphism ring of E0 cross EA. So what he did is he took this picture that we've got here, and instead of having this phi f being this isogeny that you have to construct, and what I didn't say is that you have to use huge extension fields and all sorts of nasty things. He constructed the same picture and used the same sort of constructions as Carney does, except between 4-dimensional abelian varieties, which are products of 4 supersingular elliptic curves, which allows to actually really go back to this endomorphism thing that we had with Christoph's idea. So this EF becomes an E0. I'm going to call this Iota again. So then he does the same construction, except here you've got an endomorphism again. And the degree of your endomorphism, because you're using the same kind of tricks as Carney, still needs to be B minus A. But the degree of an endomorphism, if you only use the fact that Z is in the endomorphism ring of E0, you can actually get an endomorphism of any integral norm for like E0 to the 4, just by using the fact that any integer is the sum of 4 squares. I can write down the form of the endomorphism for you if you like, but I think I should leave time for questions. And so that was the idea behind it's also called Zahin's trick. That was the idea behind Damian's attack is, okay, so you have more space in dimension 2, but actually if you go up to dimension 4, or he's actually looking at dimension 8 at some point, then you have everything you need in your endomorphism ring just by using the fact that the integers are in there and the fact that every integer is a sum of 4 squares. Okay, I think I'll stop there and take any questions.